null hypothesis is going to be that all of the means are equal to each other. And the alternative is at least one mu is different. So now we've introduced the idea of we can have words in these hypotheses. That's going to continue forward in more complicated tests as we move along. Notice there's only one null and alternative. There are no options. Previously, we had lots of options, right? We were talking about, is it a right tail test? Is it a left tail test? Is it a two tail test? We have to kind of figure out what the claim is and figure out the wording and the problem. Not here. So your life is made a little easier in ANOVA because if you identify that you have multiple means, you have one null. It's always the means are equal versus the alternative, at least one mean is different. Our assumptions. Number one, the same one you've seen every single time. We always want to check our sampling methodology. And now for all of the other assumptions that apply specifically to this test. We don't really dive into why some of these are what they are as we move forward. We did kind of explain the previous ones. Now as we move on to different tests, they have their own backstories, just like we had central limit theorem had a backstory, and thinking about what happens when you multiply n by p, right? That has its own backstory, right? We get into more complicated backstory, so we get to the point where we talk about these conditions and we kind of just say, here's what they are, just check these. Might talk a little bit about some of them, but we're not going to really stress why they're important as much as, hey, as we've talked about, every test has assumptions. It doesn't even really matter what they are. You just need to know that every test has assumptions, and you need to go find what they are for every test and make sure that they're met for every test. And if they aren't met, then our results might be a little questionable, right? To the degree that the assumptions are not valid, right? If my assumptions are really good, then my results can be really good. If they're only kind of good, my results are only kind of good. Different samples are from populations that are categorized in only one way. What that means is when we talk about groups, you can't just willy-nilly put people in different groups or observations in different groups, computers in different groups, trucks in different groups, right? Whatever we're actually measuring. They can't just be, I could put them in this group or I could put them in this group. So this bullet point here just says, make sure your groups are well defined, that they're clearly defined. Okay. These cars are made by this manufacturer. These cars are made by this manufacturer. There's no way to crisscross those because you can't be in both groups because you can't be made by different manufacturers, right? So make sure that they're all the groups are categorized in one and only one way. Second one is that samples are independent. That should seem relatively familiar because that was one of our key assumptions in our chapter 10 work, and it's the same thing here. If we have two sample mean dependent testing, that's actually a one sample test, right? We just need to make sure we work on the differences, but then a two sample independent test, which has its own way to work the problem, we had to make sure that the samples are independent. Same thing here. Now that we go to 3, 4, 5, we just need to still make sure that the samples are independent. And the last one's kind of the main mathematical assumption. We need the populations to have the same variance, and we need distributions that are approximately normal. Okay, so it's actually two things. You can break that down to the population of the same variance and the distributions that are approximately normal. I put them together because this is a loose requirement. The method is fairly robust. If you remember that term from chapter 2, the idea of robustness means when things get off a little bit, things are wonky a little bit, it's still okay. It doesn't really change much. And this is the idea here that this is a loose requirement. So as long as the variances are similar and the distributions are like kind of loosely normal, we're good to go. The method is pretty robust to deviations. It's not a huge deal. So it's kind of a, if it's bad, it'll fall apart. If the populations have really different variances, or we have some really skewed populations, it's a problem, okay? But if we're close, it'll be good enough. The method will work pretty well. What is same variance, right? If we have a difference of 5 between two variances, are those the quote-unquote same? Well, I think it depends on what the numbers are, right? If one variance is 2 and one variance is 7, I would say those are pretty different, even though they're 5 units apart, while I would say that if I have one variance of 100 and one of 105, those are close enough, even though both are only 5 apart, right? The scale matters, I guess is what I'm trying to say. So just use some common sense here when assessing if they have the quote-unquote same variance. If you see 26, 29, 31, that's close enough. But if you saw 2, 7, and 11, you'd say, oh, those are pretty far apart, right? The scale there matters. That's what I would tell you to keep in mind when you're trying to assess if things have the same variance or not. Our test statistic, we've already covered this. Again, as always, we can notate the degrees of freedom of our test statistic here with a subscript. Now we have two, so we have one comma, the other one, right? The numerator degrees of freedom, comma, the denominator degrees of freedom. And just as a reminder, what is that test statistic? Because I really want to make sure you understand what this is. Don't fall into the trap of, it's not really a big deal. I can get the numbers from Excel and then I can plug them in. Because as you've probably seen here, if you're not really understanding what you're doing, you're probably not excelling on the exams. Okay, so make sure you understand what you're doing, what this means, right? So just want to reiterate what the F statistic is. It's the variation between groups compared to within groups. Again, we're seeing what sort of spread do we have from the red to the blue to the green? Here I'm saying, well, what kind of spread did the reds just have amongst themselves? And what kind of sort of spread did the blues have within themselves? I'm comparing those two sources of variability to get my F statistic. Our rejection region p-value are going to be very similar. The one thing to note, because we only have one null and alternative, we only have one type of test, right? They are always going to be a right-tailed test. Why is that? Because the F distribution cannot even be negative, and it's right skewed. So all of our tests in this case for an ANOVA are going to be right-tailed tests. Further, when you use your F table, it should be relatively straightforward to look at, but notice the F table that you're given only has values for alpha equals 0.05. If you are interested in finding other significance levels, you are going to have to go to Excel. Again, those directions are in Canvas. It's relatively straightforward. It's just like finding a T critical value that you couldn't find in the table, except now instead of comma degrees of freedom, you have comma degrees of freedom numerator, comma degrees of freedom denominator. So it's going to work pretty similar, flipping from the T to the F in Excel. But again, this table only has alpha of 0.05, and the critical value is going to be listed in the table, and you just have to line up the intersection of the numerator degrees of freedom and the denominator degrees of freedom. You also notice that numerator degrees of freedom does not go very large, because like I said, we typically will not have crazy high numbers of groups. And the last two steps look exactly like you've seen them before. If our test statistic falls in the rejection region, our p-value is small, we reject the null. If our test statistic does not fall in the rejection region, the p-value is greater than alpha, then we fail to reject the null. In our last step, if we reject the null, that means we can conclude the alternative. If we fail to reject the null, we cannot conclude the alternative. What is the alternative? Now, the alternative is at least one of the means is actually different. And so an example, we will see more complicated examples later on. For now, just the bare bones, because this is something completely new and different. This is the type of table that you would see in an ANOVA scenario. Notice that we've got our treatment source and our error source. Again, treatment and groups are interchangeable. You could see either one. Notice we have the sum of the squares already calculated for us and the degrees of freedom calculated for us. And so we can then back calculate some things based off the degrees of freedom. Notice that we know the total degrees of freedom here are 13, which means my total sample size is 14, because my total sample size is capital N. My total degrees of freedom are capital N minus 1. So if 13 is N minus 1, that means N is 14. Similarly, my treatment degrees of freedom, that numerator degrees of freedom, is equal to K minus 1. K is the number of groups. So if I have 3 degrees of freedom, that tells me I have 4 groups. So we can kind of back calculate some different things. There we can finish the table off, which we will need to do in order to calculate our F statistic by finding the mean square in the F statistic. Just notice that there is no total mean square. There would be nothing that goes here in this box. You would only have a mean square for treatment and error, because you would take this 90 divided by 3 to get to our mean square for treatment, and then 20 divided by 10 to get our mean square error. And then the F statistic is only going to have one number, and that's going to be the ratio between the two mean squares. The null, mu1 equal mu2 equal mu3 equal mu4. Notice in the template, we put mu1 equal mu2 all the way to mu k. Well, now we know what k is. How do we get k? We talked about that earlier. based off the table, I can infer that I have 4 groups. So I stop at 4, and the alternative, no matter what, how many groups, is at least one mean is different. We haven't been given anything on assumptions. So at this point, I'm just going to say, hey, we're going to assume that our assumptions are fine. In the context of a problem, we'll get to one later where we actually see some things in the problem, and we'll dive into that. For now, we just want to be thinking about what the assumptions actually are. Our test statistic, again, we're going to label it with the appropriate degrees of freedom. So F3, 10 is always equal to mean squared treatment over mean squared error. And again, we found those previously by taking the sum of squares and dividing by degrees of freedom. The treatment mean square was 30. The mean square error was 2. And so 30 divided by 2 is 15. Our rejection region, again, I'm going to work it here, just the rejection region method, not the p-value, because the p-value you need Excel. That's not something to say that we can't do. It's just for this example, I'm only going to show the rejection region. We would draw some sort of right skewed curve, have a cutoff. This would be our shaded region for alpha. And this right here, F sub alpha, that would be the critical value. So the critical value that we would find via our table, looking at the intersection between 3 numerator degrees of freedom and 10 denominator, and notice the order matters, you can't crisscross those, would be 3.71. So in my picture, I would put 3.71 right here, and then I would draw 15 out here and say we clearly fall in the shaded region. And so because we fall in the shaded region, then we can reject the null hypothesis, meaning we can conclude the alternative that says at least one of the means is different.